And looks like everything's working like it's supposed to. All right, so today we are going to finish up section 4.5, which covers the first derivative test. And the individual steps themselves aren't too bad, at least I don't think they are. It's just remembering to put them all together. So let's say, for example, if you wanted to use the first derivative test, move this way. To find the local extrema and remember, that's just a fancy way of saying the minimum and maximum values for f of x is equal to 4 divided by 3 times x to the third power minus 7x plus 6. Okay, so remember your first step is to find your critical points. Remember, that's just where your derivative is equal to 0 or it's undefined. Okay, so we know we have our f of x right here, which means, straighten that up a little bit. There we go. Yeah, f prime of x is equal to, we have 4 over 3 times x to the third power. The derivative of x to the third power is 3x squared. So we have 4 divided by 3 times 3x squared minus 7 times the derivative of x, which is just 1, plus the derivative of 6, which is 0. You don't have to put the 0, but I'll do it anyway. Okay, so these two 3's cancel each other out. So that means that our derivative f prime of x is equal to 4x squared minus 7. So we can see there are no values of x that would make that undefined. So we can only look for values that would make that derivative 0. So f prime of x equals 0 when 4x squared minus 7 is equal to 0. Okay, so if we add 7 to both sides, divide both sides by 4, we end up with x squared is equal to 7 over 4. Then if we square root both sides, and don't forget your plus minus, that's probably one of the easiest things to forget when you square root both sides using the square root property. You have the square root of x squared, which is just x. Well, I'll go ahead and square root both sides there. That's just x is equal to plus or minus the square root of 7 over 4. I'm just going to make a little side note here. square root of 7 over 4, you can make that the square root of 7 divided by the square root of 4. Well, the square root of 7, you can leave it like that. No point in trying to simplify that one. But that square root of 4, you can just replace that with 2. So x is equal to positive or negative square root of 7 over 2. These are your critical points. Okay, so now we just have to test the values in between those critical points. So your second step is to pick test values in the intervals. And again, you don't have to do the number line. I just find it makes things so much easier when you do. So we're going to make our number line from negative infinity to infinity. We have our critical points of positive and negative square root of 7 over 2. Okay, so we'll make this negative square root of 7 over 2. We know 0 somewhere in here, so we'll make this positive square root of 7 over 2. And we can't let x equal those values, so we'll draw a little slashed line or dashed line, whichever way you want to say it, between each one. Okay. So when we pick our test values, we're actually going to plug them into our derivative. And I'll make that little side note there. So we're going to plug it into our f prime of x. Okay. So this interval here is from negative infinity to negative square root of 7 over 2. Okay, and this interval here is from negative square root of 7 over 2 to positive square root of 7 over 2. And this interval here is from the square root of 7 over 2 all the way to infinity. Okay, so we just have to pick a value in each one of those intervals. And it can be whatever value you like. So for this one, let's say we pick x equals negative 3. And again, it's completely random. You can pick whatever number you want to. And we're going to plug it into our derivative right here. So I don't like to draw too many arrows, but I'll draw a little arrow up to the derivative to kind of show that's what we're plugging it into. Okay, so f prime of negative 3 is equal to 4 times negative 3 squared minus 7. Okay, so we have 9 times 4, which is 36, minus 7, which is 29. So the derivative at negative 3 is equal to 29. We don't care so much about the value. We just care about the fact that it's positive or negative. Okay, so we know that this is positive. which means that f prime of -3 is greater than 0. So that tells us that for this interval, it's increasing. Now we pick a test value between -√7/2 and +√7/2. Well, since one is negative and one is positive, I just go to my old favorite x equals 0. And again, pick whatever value you like. Okay, so we plug that into our derivative. So f prime of 0 is equal to 4 times 0 squared minus 7. Well, that 4 times 0 squared is just 0, so we can just get rid of that right there. Which means that f prime of 0 is equal to -7. But more importantly, we know that it's negative. Which means since f prime at 0 is less than 0, we know it's decreasing. Okay, and from square root of 7 divided by 2 to infinity, I'm just going to pick x equals +3 as my test value. So that gives us f prime at +3 is equal to 4 times +3 squared minus 7. Okay. So this gives us 29, which means that it's increasing at +3. I forgot to put my little positive there. So since the derivative is positive at that point, we know that it's increasing. Okay, so we know that since, and I'm just going to kind of draw a little bit of a line across here. Since it's increasing for this interval, we know that it's going up and up and up and up and up. And it at -√7/2, we know that our derivative is 0. So we know that the slope of the tangent line is 0. So we know this is a local maximum. But only because we know on the other side of that -√7/2, it's decreasing. Because it is possible for it to increase and then increase again. So then it wouldn't be a minimum or maximum. But if it's increasing on the left and decreasing on the right, we know that's a maximum. So f prime of -3 is greater than 0. F prime of 0 is less than 0. And since we know it's increasing at +3, that means that +√7/2 is a local minimum. So local maximum is at x equals negative square root of 7 over 2. And our local minimum is x is equal to positive square root of 7 over 2. All right, so does that make sense? Any questions on that one? All right, I'll leave that up for a few more seconds. Let everybody finish up. Excuse me. All right. So let's say, for example, we wanted to use the first derivative test. To find the local extrema So sometimes instead of local extrema, they'll call it the relative extrema. Just be on the lookout for that. For f of x is equal to 4x times the square root of 1 minus 5x. Okay. Now with this one, you have to be careful because you have a square root. So whenever you're multiplying two functions and one of them happens to be a square root or a fraction with the x or the independent variable in the denominator, you want to kind of compare them to see what the overall domain is. The actual domain of x values that you can use would have to be true for both of them. So if we look at the domain of 4x, well, you can plug in any value, any real number value of x and get a real number answer. There are no undefined values of x for this one. So we know that domain is from x equals negative infinity to infinity. You can literally plug in any real number. And when we look at the domain of the square root of 1 minus 5x, well, since we're only dealing with real numbers, that means that this radicand would have to be greater than or equal to 0. So 1 minus 5x is greater than or equal to 0. So if we add 5x to both sides, we have 1 is greater than or equal to 5x. So if we divide both sides by 5, we have 1 over 5 is greater than or equal to x, or we can flip it around say x is less than or equal to 1/5. So remember, the domain we pick for the entire function would have to be a domain that would be true for both of these. So I'll make a little side note here. So if we take the domain of 4x, that's just negative infinity to infinity. So let me move this over just a little bit so I have room to write my negative infinity. Here we go. So that means every real number is okay for this one. But if we look for the square root of 1 minus 5x, I'll put that underneath it. That domain is just x is less than or equal to 1/5. So let's say this is 1/5 right here, which means everything less than that would be true, would make this a real valued function. Okay. Which means the only domain that works for both of these would be this domain right here. Because anything to the right works for 4x, but it doesn't work for this one. So we have to pick a domain for the whole thing. And that's important because it kind of, not really dictates, but leads to where we're going to pick our test values later. So we know the domain for the entire thing is just from 1/5 to negative infinity, or negative infinity to 1/5. And since 1/5 is included, you can have it equal 1/5 because this can equal 0. We're going to use our bracket. Uh-oh. All right. So now we can start going to our first and second step. We're going to find our critical numbers. Okay, remember your critical numbers, just where f prime of x is greater than 0. I mean, not greater than, equal to 0, thinking of up there. Or undefined. Make that equal to a little clearer. There we go. Okay, so since our function is the product of two functions, we have to use the product rule. So our f prime of x is equal to the first function times the derivative of the second function. And instead of the square root of 1 minus 5x, I'm going to make that 1 minus 5x to the 1/2 power. Plus the second function, 1 minus 5x to the 1/2 power times the derivative of the first times the derivative of 4x. So that means our derivative is equal to 4x times the derivative of 1 minus 5x to the 1/2 power. We're going to go ahead and use the chain rule for that one. So we bring down the 1/2 times 1 minus 5x to the 1/2 power minus 1. So 1/2 minus 1 is negative 1/2 times the derivative of what's inside. So times the derivative of 1 minus 5x, which is negative 5. Minus 1 minus 5x to the 1/2 power times the derivative of 4x, which is just 4. Okay, so we can simplify this a little bit so it's not too messy. So f prime of x is equal to, we can go ahead and combine the negative 5, the 1/2, and this 4. Okay, so 4 times 1/2 is 2. 2 times negative 5 is negative 10. So we have negative 10 times x, because we still have that x there, times 1 minus 5x to the negative 1/2 power. We can just go ahead and move that to the denominator and make that a positive 1/2 power in the denominator, or we could just rewrite it as square root of 1 minus 5x. Oh, why did I put minus there? I meant to say plus. Glad I caught that. Okay, so that should be plus. I think I was thinking of that minus there. Okay, so with this one, you can just kind of leave it the way it is. So it's plus 4 times the square root of 1 minus 5x. And I wrote that a little high purposely, only because instead of having two separate terms, sometimes it's just easier to combine them. So I'll put that over 1. Okay, so if we're going to combine them, we need a common denominator. So we're going to multiply this one by the square root of 1 minus 5x divided by the square root of 1 minus 5x, which would give us like denominators. Okay, so f prime of x will equal, since we have the same denominator, we're just going to go ahead and put that over the square root of 1 minus 5x. And then we just go ahead and add our numerators. So we have negative 10x plus 4. And if we combine those two, if we multiply those two, square root of 1 minus 5x times the square root of 1 minus 5x, well, that's the square root of 1 minus 5x squared. So the square and the square root would cancel out, leaving just 1 minus 5x. And I'll put that as a little side note. Okay, so the square root of 1 minus 5x times square root of 1 minus 5x. We can rewrite that as the square root of 1 minus 5x squared, where the square and the square root cancels out, leaving just 1 minus 5x. So that's how those two just become that one. So if we go ahead and distribute that 4, it gives us f prime of x is equal to negative 10x. 4 times 1 is 4, so plus 4. 4 times negative 5x is negative 20x, divided by the square root of 1 minus 5x. So if we go ahead and combine these like terms, we end up with our f prime of x is equal to negative 10x minus 20x is negative 30x, plus that 4 that's still hanging around, divided by the square root of 1 minus 5x. And we'll continue that on the next page. Excuse me. All right. Anyone still writing? All right. Okay, so we found our derivative. Uh-oh. Now we just have to find our critical points. Okay, so we have our f prime of x is equal to, let me bring that back up here, negative 30x plus 4 divided by the square root of 1 minus 5x. Okay, so we know that f prime of x is equal to 0 when negative 30, make that 3 a little bit neater. Negative 30x plus 4 is equal to 0. So if we subtract 4 from both sides and divide both sides by negative 30, we have x is equal to negative 4 divided by negative 30. So if we divide both of those by 2, we end up with x is equal to 215. And we'll draw a little square around that one because we have to come back to it. Okay, but we can also tell here that the derivative is undefined when the square root of 1 minus 5x is equal to 0. Okay. And with that one, we figured that out earlier. Which means that it's undefined when x is equal to, about to say 1/15, 1/5. So this just lets us know if it's undefined at x is equal to 1/5, then we know that x cannot equal 1/5. That's all that tells us. Okay. So even though 1/5 is perfectly okay for the position function, for the derivative, we can't use it. So it can't equal 1/5 for our f prime of x. For f of x, it's okay. It can equal 1/5. But for f prime of x, off limits. Okay. So since with the first derivative test, we're plugging it into the derivative, we're going to leave that out. Now, if we were plugging it into the function, that would be just fine. And we're going to plug test values into your f prime of x. Okay, so if we get our number line from, move that over a little bit so I can write my negative infinity. From negative infinity to infinity, we know we have from 2/5 and 1/5. So we can put our 1/5 right here. 2/15 and 1/5. Our 2/15, we can put that right here. And our 1/5, we can put right there. So we know this first interval is from negative infinity to 2/15. And this interval here is from 2/15 to 1/5. And it can't equal 1/5, so we go ahead and put the parenthesis there. Okay. So if you were trying to figure out why we did all that stuff at the beginning, remember the domain for the entire function is from negative infinity to 1/5. So even though it can't equal 1/5, our entire domain is only from here on to the left. Which means we're not even looking at this. Because all those values will give us an undefined function. So for that here, just put in, remember, f of x domain is from negative infinity to 1/5. Okay. So that's why for this one, we didn't have to do it on the first example we did because that was just a polynomial, and a polynomial has a domain from negative infinity to infinity. There are no undefined values for a defined polynomial. But whenever you start throwing in square roots and fractions and stuff like that, when it no longer falls under that polynomial umbrella, then you have to be a little careful. Okay. So this one, we know it can't equal 1/5, so we'll go ahead and draw our slash line. It can't equal 2/5, so we'll separate it that way. Okay, so from negative infinity to 2/15, since one's negative and one's positive, I'm just going to pick my favorite x equals 0. So we know that f prime of 0 is equal to, bring that down, negative 30 times 0 plus 4 divided by the square root of 1 minus 5 times 0. Okay. Well, negative 30 times 0 is 0, so that disappears. 5 times 0 is 0, so that disappears. That just leaves us 4 divided by the square root of 1, which is just 4 divided by 1, which is 4. So we know that f prime of 0 is equal to 4, but more importantly, we know that it's positive. So f prime of 0 is greater than 0, which means it's increasing. Okay, so from 2/15 to 1/5, I honestly had to just pick a couple of fractions and see which ones kind of fell in that interval. And I ended up picking x is equal to 1/6. Okay, so we have f prime of 1/6 is equal to negative 30 times 1/6 plus 4 divided by the square root of 1 minus 5 times 1/6. Okay, well, that gives us negative 30 times 1/6 is negative 5 plus 4 divided by, well, 5 times 1/6 is just 5 over 6. So we can make that the square root, and instead of 1, we can make that 6 over 6 minus 5 over 6. Okay. Now, a shortcut way to do this, because remember, we don't care what the answer is. We just care whether it's positive or negative. Well, what we can do here is, we know that negative 5 plus 4, that's negative. So if we have square root of 6 over 6 minus 5 over 6, that's the square root of positive 1 over 6. So we know that that's going to be positive. So a negative divided by a positive is a negative. So we just know that f prime of 1/6, make that 6 a little neater, is less than 0. Again, we don't care what the actual answer is. We just want to see if it's positive or negative for this particular test, which means it's decreasing. Okay, so we know that since it's increasing from negative infinity to 2/15, we know that is our local maximum because it's decreasing on the other side. Okay, remember this is our f prime of 0 is greater than 0, and this is our f prime of 1/6 is less than 0. Okay, so since it can't equal 1/5, it's going to go here and end up being an open circle. So the only extreme, minimum or maximum that we have here is that 2/15. So we know at x equals 2/15, that is the local maximum, local or relative maximum. All right. Any questions on that one? So again, if you have just a straight polynomial, 3x squared plus 5x plus 7 or something like that, you don't have to worry about the domain. Your domain is negative infinity to infinity, so you're good. Like I say, anytime you see a square root or a function that wouldn't by definition qualify as a polynomial, so if you have like x squared plus 1 over x, because remember for a polynomial, all of your exponents have to be positive whole numbers, 0 or higher. You can't have a fraction for an exponent. All right. Anyone still writing? Okay. Now we're going to look at the test for concavity. Okay, so what if we let f of x represent a function where the second derivative exists? A function where the second derivative of x exists on some interval from a to b. So if we know that our second derivative at c is greater than 0 for any c in that interval from a to b, then the graph is concave up. Move there. Now, if the second derivative at c is negative, for any c in that interval, then the graph is concave down. Now, if that second derivative happens to equal 0, okay, then we know the concavity is inconclusive. It's not, well, not inclusive, it's undefined. Okay. Now, at that particular point, when your second derivative is equal to 0, that's called the point of inflection. Or sometimes you just see POI. And that's just where your concave up and concave down intervals are separated. Really concave up and concave down. Intervals are separated. Uh-oh. Excuse me. Okay, now visually all this means is, let's say if you have some graph, and your graph looks something like that. Make that a little longer. Okay. So we can see that this interval here is concave down. And this interval here is concave up. Okay. Now, somewhere in between those is some point C. And we know concave down, of course, your second derivative is less than 0. Your concave up, your second derivative is greater than 0. But at this one, your second derivative is equal to 0. And that's your point of inflection. Let's say it's some value C. All right, anyone still writing? All right. So let's say, for example, we wanted to find the x value of the point of inflection for the graph of f of x is equal to negative 3x to the third power minus 5x squared minus 9x minus 2. Okay, so we know that the point of inflection is just where the second derivative is equal to 0. So we know that our first derivative, the derivative of negative 3 times x to the third power, we bring down the 3. So negative 3 times 3 is negative 9 times x to the power of 3 minus 1, so it's squared. Minus the derivative of 5x squared. So we have negative 5 times the derivative of x squared. We bring down the 2. So negative 5 times 2 is negative 10 times x to the power of 2 minus 1, which is just 1. Minus 9 times the derivative of x. We know the derivative of x is just 1. So negative 9 times 1 is just negative 9. And the derivative of 2 is just 0 because it's constant. Okay, so we have the first derivative. Now we take the derivative of that derivative. So the derivative of x squared, bring down the 2. Negative 9 times 2 is negative 18 times x to the power of 2 minus 1, which is just 1. So we can leave it like that. Minus 10 times the derivative of x. Derivative of x is 1. So negative 10 times 1 is just negative 10. Minus the derivative of 9. Derivative of 9 is just a 0, so that disappears. So we know that's our second derivative. Okay. So we know that our second derivative is equal to 0 when negative 18x minus 10 is equal to 0. So if we add 10 to both sides and then divide both sides by negative 18, we have x is equal to 10 divided by negative 18. Well, we can divide both of those by 2 to simplify, or multiply them by 1/2. So we know x is equal to negative 5/9. And that's the x value of the point of inflection. Oops, straighten that up a little. There we go. Now, if they want to know the y value, you just get that and plug it into your original function. So let's say the y value can be found plugging x equals -5/9 into your original function, f of x. But this question didn't ask for it, so I'm not going to really worry about that one. All right. So let's say, for example, if we wanted to determine if f of x is equal to 3x to the third power plus 7x squared plus 9x minus 2 is concave up or concave down, at x is equal to 1. Okay, so for this one, you just have to remember the second derivative is greater than 0 at some point c. Then we know it's concave up. And if the second derivative is less than 0, we know it's concave down. Okay, so we know our f prime of x is equal to the derivative of x to the third power, bring down the 3. So 3 times 3 is 9, times x to the power of 3 minus 1, that's 9x squared, plus the derivative of x squared, we bring down the 2. 7 times 2 is 14, times x to the power of 2 minus 1, which is just to the first power, so we can leave that the way it is, plus 9 times the derivative of x. The derivative of x is just 1, so 9 times 1 gives us 9, minus the derivative of a constant, which is 0, so that just disappears. Okay, so now we find our second derivative by taking the derivative of the first derivative. The derivative of x squared, we bring down the 2. So 9 times 2 is 18, times x to the power of 2 minus 1, which is just the first power, plus 14 times the derivative of x. So that's 14 times 1, which is 14. And the derivative of 9 is 0, so that disappears. Okay, now at x is equal to 1, our second derivative at 1 is just 18 times 1 plus 14, which is 32. So we can see that the second derivative at 1 is positive. So we know it's concave up at x is equal to 1. Bring that up a little bit. Any questions on that one? All right. Okay, so that brings us to our second derivative test. Okay, so what if we have a function where we know that the first derivative at some value c is equal to 0? Where we know in that interval c is somewhere between some value a and b. And we also know that the second derivative exists. I clean that up a little bit. Oh, forgot I even put that on there. On some interval from a to b. Okay, well, we know that if the second derivative at c is greater than 0, then the position function at c is a local minimum. Or remember, it could be relative minimum. But if the second derivative at that value c is negative, let's write then instead of the, then we know that f of c is a local maximum. And again, it could be relative maximum. Okay. Now, the only thing with the second derivative test is that if the second derivative is equal to 0 at some value c, then the test really doesn't tell us anything. The test is inconclusive. And when it fails, that just means that we have to use the first derivative test to find the answer. Use the first derivative test. And kind of a quick overview of the first derivative test. After you find your critical points, if the derivative, f prime, goes from negative to positive, then we know that f of c is a local minimum. But if your derivative goes from positive to negative, then we know that f of c is a local maximum. Now, if that derivative doesn't change at all, you get to the critical point and it's increasing on the left and then it continues increasing on the right, or decreasing on the left and decreasing on the right. So if it does not change, then we know that f of c is not a local minimum or maximum. It's neither a local minimum or local maximum. Let's straighten that up a little bit. There we go. All right. So let's say, for example, we wanted to find the x coordinate or coordinates, depending on how many you have, for all local minima given by the function f of x is equal to x to the 9th power plus 3x to the 8th power plus 2. using the second derivative test. So first thing you have to do, you have to find your critical points. Which in this case is just where your first derivative is equal to 0 because it's a polynomial, so there are no undefined values. Okay. So our f prime of x is equal to the derivative of x to the 9th power. Let me make that 9 a little smaller so it actually looks like an exponent. There we go. So we bring down the 9 and subtract 1, so that's 9x to the 8th power, plus the derivative of 3 times x to the 8th power. We bring down the 8. 8 times 3 is 24 times x to the power of 8 minus 1. And make that a little smaller. Here we go. Okay, so we know that first derivative equals 0 when 9x to the 8th power plus 24x to the 7th power equals 0. Okay, now with this one, it'll be a whole lot easier if you just take out the greatest common factor. So we could factor out a 3x to the 7th power from each one. That leaves us with 3x plus 8. So that means this could be true when 3x to the 7th power is equal to 0, or 3x plus 8 is equal to 0. Either one of those could make this true. So 3x to the 7th power is only equal to 0 when x is equal to 0. So if we subtract 8 from both sides and divide by 3, we know that x can equal negative 8 over 3. Okay, so these are your critical points. Now, for the second derivative test, you're going to plug these into your second derivative. And make that a little, move that down a little so it's not. There you go. That second derivative is a little bit clear. or a little clearer. Okay, so plugging it into your second derivative, that'll be our second step. So we have to find our second derivative, which we'll just find the second derivative off this form, because this form we'd have to use the product rule and don't want to go through all that. So it'll just be a little easier to do it off this one. Okay, so our second derivative is equal to, we bring down the 8. 9 times 8 is 72 times x to the 7th power. Plus, we bring down the 7. 7 times 24 is 168 times x to the 6th power. Okay. And again, just to make it a little easier to work with, you don't have to do this, but it can be helpful sometimes to just take out the greatest common factor. So with this one, 24x to the 6th power is the greatest common factor. And that leaves 3x plus 7. Okay. So what if we plug in x is equal to negative 8 over 3 into our second derivative? Bring that up a little bit. That means our second derivative, x is equal to 24 times negative 8 over 3 to the 6th power times 3 times negative 8 over 3 plus 7. Okay, so the 3's here cancel each other out. So our second derivative, I forgot to put my negative 8 over 3 inside of here. Doesn't matter, but might as well be consistent here. So make that f double prime of negative 8 over 3. So that gives us 24. And I'm not even going to bother with this part. I'll show you why in a second. 8 over 3 to the 6th power times negative 8 plus 7. We can see here we have two functions being multiplied to each other. Well, I guess you could say two factors being multiplied. If you take a negative number and raise it to an even exponent, it's going to come out to be positive. So negative 8 over 3 to the 6th power is going to be some positive number. So some positive number times positive 24 is going to end up being some positive number. And negative 8 plus 7, well, that's just negative 1, which we know is a negative number. So positive times a negative is a negative. So we don't even have to work all of this out. We just need to know whether it's positive or negative. Negative 8 over 3. We know it's less than 0. So we know at that point, it's concave down. So we know when it's concave down, we know that, so x equals -8/3 is a local maximum. Whoops, there we go. And we'll continue on the next page. And remember, when it's concave down, that point is your maximum. Okay. Now let's look at our second critical point where x is equal to 0. Bring it down. There we go. Okay. So we know that for x is equal to 0, if we plug that into our second derivative, we know our second derivative at 0 is just going to be 24 times 0 to the 6th power times 3 times 0 plus 7. Which just gives us 0 times 7, which is 0. So we know that when the second derivative at any point is equal to 0, the second derivative test fails. Yep. And we're going to use the first derivative test. Okay. Now, we don't have to do the entire domain of the interval because we already know that -8/3 is a local, there you go, is a local maximum. So we just have to do to the right of that since that's 0. So we know if it's a local maximum, it goes up on the left, down on the right. So for this one, to do the first derivative test, we just have to worry about x equals 0. But we don't have to go all the way to -infinity. We just have to worry about -8/3 to 0. Because we already know what goes on over here. And this interval is from 0 to infinity. Okay. We know that we can't equal these values, so we'll go ahead and draw our little dotted line separating them. Actually, I'll give this a little more room so I'm not cramming all the work into such a small space. do it. There we go. Okay, so from -8/3 to 0, I'll pick x is equal to -1. Okay, so since we're using the first derivative test, remember, we're plugging this into the first derivative. You only plug it into the second derivative when you're doing the second derivative test. Okay, so we know that f prime of x is equal to 3x to the 7th power times 3x plus 8. Well, if we plug in x is equal to -1, f prime of -1, here we go, is equal to 3 times -1 to the 7th power times 3 times -1 plus 8. Okay. And again, you can calculate the whole thing if you want to, or you could just separate it by each factor. Okay. So we know -1 to the 7th power, well, a negative number to an odd exponent is always going to be negative. So you have a negative number times 3, which is negative, times 3 times -1 plus 8 is +5, so we know that's going to be positive. So a negative times a positive is a negative, so we know that f prime of -1 is less than 0. So we know it's decreasing. Make that a little longer. And from 0 to infinity, I just pick the simplest one. So I'll pick x is equal to 1. And that looks too much like an E. Clean that up a little. There we go. So we plug that into our first derivative. So f prime of +1 is 3 times 1 to the 7th power times 3 times 1 plus 8. Uh-oh, ran out of pencil lead there. There we go. Okay, and again, this one's positive and this one's positive. So we know the first derivative at 1 is positive, which means it's increasing. So if it's decreasing on this interval and increasing on this interval, then we know right here at 0 is a local minimum. So we know that x equals 0 is a local minimum. And remember, we already did this part of it. So -8/3 is a local maximum, so we know that it's increasing on the left and decreasing on the right. Oh, that should line up a little bit better than that. Line it up, and here we go. That's a little better. So the graph would have somewhat that shape. Any questions on that one? All right. Okay, now we'll go ahead and start on section 4.6. And I'll freeze that in case anyone's still writing. Oops. Good. Anyone still writing? Okay. Okay, now section 4.6 covers limits at infinity. Okay, now this section mostly looks at the end behavior of a function. The end behavior of a function over an infinite interval. Okay, so let's say, for example, if we had f of x is equal to 3x squared over x squared plus 1. As x approaches infinity and negative infinity. Okay, so just to help visualize, we're going to go back to our table. Okay, and right in the middle, we're going to start at 0. And we know when x is equal to 0, this whole thing is equal to 0. So let's say this is your x and your f of x. Okay, so let's say if we let x equal 1. Okay, we plug in x equal 1, we have 3 divided by 2, which is 1.5. What if we plug in x is equal to 10? We have 3 times 10 squared divided by 10 squared plus 1, which would give us 2.97. We let x equal 100. Well, that gives us 3 times 100 squared divided by 100 squared plus 1. Plug that into your calculator and you get 2.9997. And as you plug in bigger and bigger numbers towards infinity, your y value just gets closer and closer and closer to 3. Okay, so this is our x approaches infinity. Now, if we went the other way and approached negative infinity, again, if we plugged in -1, we'd end up with positive 1.5 because the squares just make them positive. If we plugged in -10, we'd still end up at positive 2.97. If we plugged in -100, we'd still end up at positive 2.9997. So if you kept plugging in negative numbers approaching negative infinity, your y value would just keep getting closer and closer and closer to positive 3. So if we were to graph this one, and I'll just make our x and y axis. We can see that no matter how far we raise or lower, in this case, our x value, our y value will never actually reach 3. It'll get infinitely close, but it'll never reach 3. So this is our 3 right here. So this graph will look somewhat like this. Where it'll just keep getting closer and closer and closer to 3. We know the limit of f of x as x approaches negative infinity is equal to 3. And we know the limit of this function f of x as x approaches positive infinity is equal to 3. Excuse me. Okay. Now in this case, y equals 3 is your horizontal asymptote. Horizontal asymptote. For the function f of x is equal to 3x squared divided by x squared plus 1. All right. Which brings us to our definition. Okay. So we know that the line y is equal to some value we will call L. Is a horizontal asymptote of the graph of f of x if, first condition, the limit of f of x as x approaches infinity is equal to L, or the limit of f of x as x approaches negative infinity is equal to some value L. Now notice here we said or, which means that it could be both, but it doesn't have to be. So you saw in the previous example, both had a limit of 3, but it would have been the same if just one of them had a limit of 3. So it does not have to be both. But it could be. Okay, so you could have one of those equal L or both equal L. It would still be the horizontal asymptote. Okay. Now, for a lot of these questions, you want to be able to remember if you have the limit of some constant divided by some value that's getting bigger and bigger and bigger, it's going to equal 0. Or the limit of some constant divided by some value that's approaching negative infinity is also going to be 0. So R is just a positive real number. And C is a constant. So let's say, for example, if we wanted to evaluate the limit as x approaches infinity of 5 minus 2 over x squared. So I'm just going to rewrite that. 5 minus 2 over x squared. And by the limit properties, we're just going to go ahead and distribute that to both terms. That gives us the limit of 5 as x approaches infinity minus the limit of 2 over x squared as x approaches infinity. Okay. Well, we know the limit of a constant is just that constant. So the limit of 5 is just 5. Minus the limit of a constant divided by a number that's getting bigger and bigger and bigger and bigger and bigger, that limit approaches 0. So it's just 5. Right. Let's say, for example, we wanted to evaluate the limit Let's say we have the limit as x approaches infinity of 2x minus 1 divided by x plus 1. Okay, so what if we have, I'm just going to rewrite it, x approaches infinity, so 2x minus 1 over x plus 1. And we rewrite that using our limit properties. So we can take the limit of the numerator of 2x minus 1 divided by the limit as x approaches infinity of x plus 1. Okay, so we know that as x gets bigger and bigger and bigger and bigger and bigger, our numerator just gets bigger and bigger and bigger and bigger and bigger. And as our denominator gets, well, as x gets bigger and bigger, our denominator would just keep getting bigger. So that's infinity over infinity, which really doesn't give us an answer because that's called an indeterminate form. I knew that wasn't going to fit when I started writing. I just had to try it. I'll put it down here so I have a little more room. Indeterminate form. Okay. But we can still get an answer from it. Because if you notice, the largest exponent for your variable is to the first power, or x to the first power. So what we're going to do is we're going to divide each term by x to the first power, or just x. So that gives us the limit as x approaches infinity of 2x divided by x minus 1 divided by x divided by x divided by x plus 1 divided by x. So we just took every term in our original limit and divided each one of them by x. Which is just the same as multiplying the numerator and denominator by 1 over x. Okay, so we see these two x's cancel each other out. These two cancel each other out and become 1. That gives us the limit of 2 minus 1 over x divided by 1 plus 1 over x as x approaches infinity. Now the next step, you can skip it, but I'm going to write it out anyway. But here, you're just going to take the limit of the numerator and denominator, and we're just going to distribute it. So you have the limit of 2 as x approaches infinity minus the limit of 1 over x as x approaches infinity divided by the limit of 1 as x approaches infinity plus the limit of 1 over x as x approaches infinity. Okay. So again, I wrote it out, but you can kind of go from this step to the next one. And once you get comfortable, skip that one. Because you can just say the limit of 2 is just 2. Minus the limit of 1 over x, again, a constant divided by a number getting bigger and bigger and bigger is always going to have a limit of 0. Divided by the limit of 1 is just 1. Plus the limit of a constant divided by a number getting bigger and bigger, it's going to be 0. Like I said, this is good for showing why you can skip it, but you can really skip it. So that gives us 2 over 1 or just 2. Make that 2 a little neater. There we go. So at that infinity over infinity, not too unreasonable to think that the limit would be infinity, but it wouldn't be all the time. Sometimes it is, but no guarantee it would be. All right, any questions on that one? All right, so let's look at the first example we did when we filled out that table and found that the limit was 3. So we wanted to evaluate the limit of 3x squared divided by x squared plus 1 as x approaches infinity. Oh, negative infinity. Whether we can do it for infinity or negative infinity doesn't matter. Okay. So again, we saw that if we have the limit as x approaches negative infinity of 3x squared over x squared plus 1, we take the limit of the numerator. As x gets bigger, this number just keeps approaching infinity. We take the limit of the denominator. As x gets bigger, that denominator just approaches infinity. Okay. Which, like I said, doesn't really give us an answer. So we look for the largest variable exponent, which in this case is x squared. So now we're just going to divide each term by x squared. Okay, so we have the limit as x approaches negative infinity of 3x squared divided by x squared divided by x squared divided by x squared plus 1 divided by x squared. Okay. So again, the x squared cancel each other out. Okay, so we have the limit of our numerator. So that gives us the limit as x approaches negative infinity. Make that infinity a little neater. Of 3 divided by 2x squared canceled out down there. That's the limit of 1 as x approaches negative infinity plus the limit of 1 over x squared as x approaches negative infinity. Make that x a little smaller. There we go. And again, this is the step you can skip because you can kind of figure it out just from the previous step. Okay, so we know the limit of 3 is just 3 divided by the limit of 1 is just 1 plus the limit of 1 over x squared is just going to be 0. So that's just 3 over 1, which is just 3. So it'd just be a lot easier to do it this way than drawing out the table and plugging in values and taking 10 minutes on that one. All right, any questions on that one? All right, so as long as your numerators and denominators are polynomials, it usually goes pretty smoothly. The only ones that might give you a little bit of trouble are the ones with square roots in the numerator or denominator, but it's really a quick fix around those. So what if we wanted to evaluate the limit as x approaches infinity of 3x minus 2 divided by the square root of 2x squared plus 1. Excuse me. Okay. Now with this one, because you're dealing with a square root, you want to remember that the square root of x squared is just equal to x. Okay. So if we take our limit of 3x minus 2 divided by the square root of 2x squared plus 1, the numerator, we can divide each term by x. Our denominator, we can divide each term by the square root of x squared, which is an equivalent value. but it helps us in that form solve it a little bit easier. Okay, so if we look at our numerator, let's have the limit as x approaches infinity. We have 3x. We're going to divide that by x. Minus 2 divided by x. Divided by the square root of 2x squared plus 1. We're going to divide that whole thing by the square root of x squared. Now, the only reason I didn't jump and immediately divide both of those by square root of x squared, because I didn't want to skip any steps. So if we have the square root of 2x squared plus 1 divided by the square root of x squared, and we know if we have a square or any nth root divided by the same index nth root, we can just put them both under the same quotient. So it's 2x squared plus 1 divided by x squared. Okay. We've been kind of doing that all along, but we've been mostly doing it in reverse, taking one big square root fraction and separating it into two square roots. But this time we're doing it in reverse. So that means we can rewrite this as the square root of 2x squared over x squared plus 1 over x squared. Where these two x squared cancel each other out. So that gives us the square root of 2 plus 1 over x squared. Uh-oh. So that means we can rewrite this denominator as that. Okay. So if we look at our numerator, we know these two cancel each other out. That gives us the limit as x approaches infinity of 3 minus 2 over x divided by the square root of 2 plus 1 over x squared. Okay. And again, this next step you can skip once you're comfortable with it. We're just going to take the limit of each term. So we have the limit of 3 as x approaches infinity minus the limit of 2 over x as x approaches infinity divided by the limit of the square root of 2 plus 1 over x squared as x approaches infinity. Okay, so we know the limit of 3. Well, the limit of a constant is just that constant, so that's just 3. minus the limit of a constant divided by a number getting bigger and bigger and bigger. It's just going to be 0. Divided by, you can take, if you have the limit of a square root, if you want, you don't have to do this, but you can rewrite it as the limit of 2 as x approaches infinity, plus the limit of 1 over x squared as x approaches infinity. Again, it's optional to rewrite it like that. You could just take the limit of 2 and the limit of 1 over x squared. Which way you do it is completely a personal choice, whichever way you're most comfortable with. Okay. We know the limit of 1 over x squared, any constant divided by a number getting bigger, is just going to be 0. And the limit of 2 is just 2. So the 3 minus 0 is 3. Divided by the square root of just the limit of 2 is just the square root of 2. Now, they may want you to rationalize your solution, which means not have any square roots in the denominator. So what we're going to do is take that and multiply it by square root of 2 over square root of 2. Okay, so 3 times square root of 2 is just 3 square root of 2. And the square root of 2 times square root of 2 is the square root of 2 squared, which is just 2. So again, they may ask you to rationalize it. So it could be this way or this way, depending on which way they want the answer written. All right. Any questions on that one? Okay. So remember, you're always going to divide each term by the largest largest variable exponent. And in this case, they had the same one, just written a different way. Bring that down a little bit. There we go. All right. What if we want to look at polynomials at infinity? Okay. Now, with the polynomials at infinity, with those, you're just going to focus on the leading term. Just like with you did back in intermediate or pre-algebra or pre-calc. But then you did when the first term is negative, the leading coefficient is negative, it's concave down, or you know that the endpoints are both pointing down. When it's positive, you know they're both pointing up. Okay, but with this one, you know, for limits of polynomials, as x approaches either positive or negative infinity. Same thing for both. We want to just focus on the leading term. That leading term tells us everything we need to know about the endpoints. Okay, so let's say, for example, we want to find the limit for, let's say, the limit as x approaches infinity of negative 2x squared plus 5x minus 10. Okay, so remember, we're just going to focus on the leading term. So you have the limit as x approaches infinity of negative 2x squared, and the rest doesn't even matter. We don't even care what those are. We're not even going to put them there. We're just focusing on this leading term. And in that leading term, we're going to look at each factor. We're going to look at that x squared and that negative 2. Okay, so first let's look at the x squared. So as x approaches infinity, that just means that x squared just becomes a really big positive number. Because if you plug in 5, you get 5 squared. If you plug in a billion, you get a billion squared. So no matter how big the number is, it's just going to end up being a really big positive number. It becomes a really big positive number. Clean that up a little. Okay, so if you take negative 2 times a really big positive number, then that just becomes a negative number with a very large absolute value. So it's going to end up being a negative number because you have a really big positive number times negative 2. So negative 2x squared means that a really big positive number which in this case is your x squared, is multiplied by negative 2. So that negative 2x squared is just a negative number times a really big positive number. Well, I'll say almost infinitely large positive number. Large positive number. Just to kind of make sure that's accurate. Can't say infinitely because there's no such value as infinity, so say almost infinite or approaching infinity. So if you have a negative times a positive, that's just going to equal a negative number. With a really large absolute value. With an almost infinite absolute value. Which is just negative infinity. Just a very long-winded way of saying negative infinity. So again, you don't have to write all of this. This is just the explanation portion of it. So that's more of a note. So we know that the limit of negative 2x squared plus 5x minus 10 as x approaches infinity is equal to negative infinity. All right, any questions on that one? All right. So let's say, for example, if we wanted to evaluate the limit as x approaches negative infinity of negative 6x to the third power minus 2x squared minus 4x plus 5. So again, we're only going to focus on the leading term. So we're just going to look at the limit as x approaches negative infinity of negative 6x to the third power minus, and it doesn't even matter what the rest of it is because we're just focused on this one. That's going to tell us everything we need to know about the end behavior. Yes?
Yeah, it's x versus negative infinity.
Oh, thank you. Thank you. I didn't even realize I did that. Okay. So again, we look at each one of those separately. Okay. So we know as x approaches negative infinity, x to the third power will result in a negative value. With an almost infinite absolute value. So kind of think of negative 1 to the third power. Negative 1 times negative 1 times negative 1 will give you a negative number. Any negative number, negative real number, multiplied to itself 3 times will give you a negative number. So if you have an odd exponent, you're going to end up with negative. That's if you're approaching negative infinity. Because negative a billion times negative a billion times negative a billion will still be a negative number. Okay. So that means if we have negative 6 times x to the third power, you just have that really large, I just can't say large value, but negative value with a large absolute value multiplied by negative 6. So here you just have a negative number times a negative number. I'll say number. I don't want to use value over and over again. Negative number with a large absolute value. I don't know, large doesn't even seem to cut it. Let's say almost infinite just seems a little more accurate. Large just seems to downplay it. almost infinite. There you go. It's a little more accurate. Okay. So here we just have a negative number times a negative number, which is going to be a positive number with an almost infinite absolute value. Because we know that a negative times a negative equals a positive. So that means we know that the limit as x approaches negative infinity of negative 6x to the third power minus 2x squared minus 4x plus 5 is equal to infinity. All right, any questions on that one? And again, this part here, you don't have to write it out each time you solve it. This is just a visual of the thought process behind it. All right. Now, what if we wanted to evaluate the limit as x approaches infinity of sine of x over x? So whenever you have any type of trig limit, it helps to, won't help all the time, but probably 90% of the time, 95% of the time, if not more, starting off with the squeeze theorem helps. Or the sandwich theorem, depending on which text you look in. Just two different names for the same principle. So we start off with sine of x. Well, we know that sine of x just bounces between -1 and 1. All the values for sine of x fall in that interval. So -1 is less than or equal to sine of x, which is less than or equal to 1. And you do the same thing for cosine. With tangent, it would be negative pi over 2 to pi over 2. Okay. Now the function we're looking for is sine of x over x. So we're just going to divide each one of those terms by x. Because the whole goal is to get that middle term to look just like the function we have up here. So that gives us -1 times 1 over x, which is -1 over x, is less than or equal to sine of x. Uh-oh, should have made that a little higher up. Over x, which is less than or equal to 1 over x. Now the function matches with the function that we have to evaluate. So now we just have to find the limit as x approaches infinity for each one of those sections. So we have the limit as x approaches infinity of -1 over x, which is less than or equal to the limit as x approaches negative infinity of sine of x over x, which is less than or equal to the limit as x approaches negative infinity of 1 over x. So again, we know the limit of a constant divided by a number getting bigger and bigger and bigger is just going to be 0, which is less than or equal to the limit as x approaches negative infinity of sine of x over x. Which is less than or equal to the limit of a constant divided by a number getting bigger and bigger and bigger, even in the negative direction, getting negative bigger and bigger and bigger. It's just getting really, really close to 0. Oh, why did I put that negative there? So that should be infinity. I have no clue why I put that negative there. I think I was still thinking about the previous problem. So it should be positive infinity. Even though you'll get the same answer for both, it's still. Okay. Now, if the limit below it is 0 and the limit above it is 0, then it's safe to say by the squeeze theorem that this limit is 0. So we know that the limit as x approaches infinity of sine of x over x is just 0. And if you remember in chapter 2, one of the special trig identities, where I said, okay, we're going to prove it later, but just trust me, this is what it's equal to. If you go back, that's what it's equal to. That's one of them. I just said we're going to prove it later, but right now, just trust me that it equals this. So this is the proof of that one. So you can use it without reservation. All right, any questions on that one? All right, so we will go ahead and stop there. And tomorrow we will start on 4-7. Just applying all this good stuff to, I guess you can call them story problems. So I'll start on 4-7.
For the second exam, I got a problem marked wrong, even though my answer was the same as the